up to this point, we've spent most of our time finding derivatives, and now we want to look at antiderivatives. And what that means is if we have a function and whose derivative we know, or if we know the derivative of a function, we want to be able to find the original function. Okay, so it's kind of the opposite of taking a derivative. We want to take a derivative and we want to find the original function. Now function f, capital F, is an antiderivative of lowercase f on an interval I if capital F prime of x is equal to little f of x for all x and I. We want to find an antiderivative for each of the following functions. Now, notice we have f of x equals 2x, so we want to find a function that has the derivative 2x. Now, that's going to be a power rule. If I had x to the positive 2, and I take its derivative, then we bring a 2 to the front, subtract 1 from the exponent, and our derivative is 2x. So the antiderivative of 2x is x squared, because that's a function whose derivative is 2x. An antiderivative of the cosine of x is sine x. Remember our rules, the derivative of the sine of x is cosine x. Here I have two terms, so I'll need to find the antiderivative of each. The antiderivative of 1 over x, remember, was the natural log of the absolute value of x. And here we have 2e to the 2x. And remember, if you have e to the u, and I take its derivative, then that is e to the u times du dx. So the derivative of 2x is 2, which we have right here. So the antiderivative is e to the 2x. Because that derivative would be e to the 2x times the derivative of 2x, which is 2, or 2e to the 2x. Now if we want to look at the most general antiderivative, if capital F is an antiderivative of f on an interval I, then the most general antiderivative of little f on I is capital F of x plus c, where c is an arbitrary constant. What that means is if we take any of these examples, like for the first one, if I had x squared plus 5, and I took its derivative, then that would be 2x plus 0, or 2x. Or I could have had something like capital F of x equals x squared minus 3. If I took its derivative, that would be 2x. Derivative of negative 3 is 0. So I could sit here all day and just list off functions that have derivatives of 2x by just adding or subtracting any constant. I was adding and subtracting integers. I could add and subtract fractions or decimals. It doesn't necessarily even have to be integers. So the most general antiderivative uses a plus c, and the plus c just denotes an arbitrary constant. So here if we want to find an antiderivative of little f of x equals 3x squared, first thing we need to think about is it is a power rule, and if it's now a 2, it was before a 3. The derivative of x cubed would be 3x squared. But now we want the most general, so we'll put plus c. Now this gives us a certain condition. It says that capital F of 1 is negative 1. Remember, capital F of 1 is what we get when we plug 1 in for x. And that should be negative 1. Well, 1 cubed is 1. If I subtract 1 from both sides, I'll get negative 2. So my antiderivative here would be x cubed minus 2. If I take its derivative, I would have 3x squared. The derivative of negative 2 is 0. If I plug 1 in, I will have negative 1. Now, here it shows us a graph of y equals x cubed plus c, and where c is negative 2, negative 1, 0, 1, and 2. Now, at any point along this graph where x is, or along these graphs where x is equal to 1, you'd actually have exactly the same slope. So we needed to know a specific point there. You know, this graph has the point 1, negative 1. Otherwise, it could be any of these graphs because they all have the same shape. They're just the same graph shifted up and down. Now here is a table that gives us some general antiderivatives. And we have the power rule basically in reverse, and the rule for sine x in reverse, and cosine x in reverse. And this is very helpful as you go through and you try to find antiderivatives. Now let's look at a few examples. Let's take f of x equals x to the 5th, and we want to find the general antiderivative of each one of these functions. Now this is the power rule, x to the n, and it said we take 1 divided by n plus 1, x to the n plus 1, plus c. So that means we have 1 divided by 5 plus 1, x to the 5 plus 1, plus our constant. Of course, 5 plus 1 is 6, so we would have 1/6, x to the 6, plus our constant. Now, the reason we do this part is remember that when we take the derivative, we bring the 6 out and make it a coefficient. Well, notice there's no coefficient here. So in order for that 6 to cancel out, I would need 1/6. 6 times 1/6 is 1. Of course, we subtract 1 from our exponent, we get 5. And no matter what our constant is, the derivative of our constant would be 0. It's real easy to check these. We just check by taking our function, taking its derivative, and making sure this is what we get. Now the second part here is also a power rule. We need to think about that as x to the negative 1/2. So that would be 1 divided by negative 1/2 plus 1, x to the negative 1/2 plus 1, and of course plus c. Negative 1/2 plus 1 is positive 1/2. So I have 1 divided by 1/2, x to the positive 1/2, plus c. If you'll multiply top and bottom of this fraction by 2, that will give us 2 on top and 1 on bottom, so we will have 2 x to the 1/2 plus c. Now, of course, the plus c, the derivative is going to be 0, but if we look at this part, we'll have 1/2 times 2 is 1, and subtract 1 from the exponent, and we'll have x to the negative 1/2. Now let's look at this one. We have sine of 2x. Now go back. If we have sine of 2x, that's negative 1 over k cosine of kx plus c. Now the reason that happens is this is going to be a chain rule. Remember, when we take the derivative of cosine of x, we get negative sine x, so that's where the negative comes from. And when we do the chain rule, we'll have to take the derivative of kx, which is k. So this would be negative 1 over 2 cosine of 2x plus c. Now the reason this works is, when I take this derivative, the derivative of the cosine of x is negative sine x, so those negatives cancel. Or negative sine 2x, so those would cancel. Then I have to take the derivative of the 2x, which is 2. And so the 2 times 1/2 will cancel out. Now let's take this, and we probably want to treat this so that we know what our k is as 1/2 x, the cosine of 1/2 x. Okay, now let's go back. Cosine had a similar formula. It's 1 over k sine kx plus c. So I would have 1 over k, 1 over 1/2, sine of 1/2 x, or x over 2, plus c. Now, same as above, if I multiply both top and bottom by 2, I will have 2 sine of 1/2 x, or if you want to go back and make it x over 2 again, plus c. Because remember, when you take this derivative, you have to do a chain rule. The derivative of sine of x is cosine of x. So the derivative of sine of x over 2 would be cosine of x over 2, but you'll need to multiply by the derivative of x over 2. Now let's look at this one, e to the negative 3x. And let's go back to our formulas again. E to the kx is 1 over k, e to the kx plus c. So that's going to be 1 over k, and our k is negative 3, e to the negative 3x plus c. Now we generally don't leave a negative in the denominator, so I'm just going to pull that out into the front. So that's negative 1/3, e to the negative 3x plus c. Because here the derivative of e to the x is e to the x. So e to the negative 3x would be e to the negative 3x times the derivative of negative 3x, which is negative 3.